Welcome to part 6 of Competency 16. In this video, we will work with probability applications. Number 1, how many different ways can all the letters of the word banana be arranged? Okay, this is a permutation. It isn't actually probability, but it is quite related to several probability, situations. So anyway, what we need to note is the word banana, although we're worried about its arrangement, it does have repetition. So this is how we need to think of it. We need to think of the total permutation divided by the permutation of repetitions. Okay. So, or rather, we could call that the combination of each repetition. All right. So let's look at what that would be on our calculator. Okay. First, we need to know how many letters does banana have? Okay. So we have 2, 4, 6. No, I'm sorry. 1, 2, 3, 4, 5, 6. It has 6. Okay. Or you could count by twos. Doesn't matter. So we know that n equals 6. Okay. That's our number of letters. Right now, repetition. Well, I see A has 3 and N has 2. Okay. That way we can see what we're looking for here. So we can, I just want to draw that a little bit better. So you see, that's what we're looking for. Okay, so let's just pop in the calculator. Don't even, write it out. Let's put it in the form that we're given for that repetition. Remember, we're looking for total permutation divided by permutation of repetitions. Okay, so let's say alpha window. Oh, no, wrong one. I jumped ahead of myself. It doesn't matter. I just arrow over and it gives me my fraction. We need the fraction first. Now let's do the alpha window. Alpha window. And we need number 7. So our total is 6. So that'll be 6 out of 6. We want everything included. Okay. Nothing being pulled out. Now let's arrow down to our denominator. We have 2 repetitions. We have one that has a count of 3 and one that has a count of 2. Okay, well, that's alpha window, and we're talking number 7. So let's do our 3 out of 3, 3 out of 3. Then we arrow over, say, times. Okay, we multiply. All right, then alpha window number 7 again. And we need 2 for the n. So that's 2 out of 2. Now let's push enter. And our value we need is 60. Okay. All right. That is option A. All right, let's look at number 2 now. Okay. All right, we're going to do the same thing, but that's quite a few more letters to concern ourselves with. So let's start with I. Let's see, that's 1, 2, 3, 4. Okay. And let's see, S, we have 1, 2, 3, 4. So we have 4, 4. Now let's see, P. Okay, and that one, I'm going to do a little, well, do the best I can there to mark it. You know what? Maybe a different color. Yeah, let's do that. Let's just pick a different color here. There's 1, 2. Okay, so we have 4, 4, and 2, the values of repetition. Now, whoa, we didn't even count how many total we had here. Let's see. I see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So n equals 11 equals 11. And then we have a repetition that is 4 letters, and then we have another repetition with 4, and then we have a final repetition that has 2. All right, let's set that up in our calculator. We're going to set it up just as we did above. Okay, now you could type all that back in again, or we can simply arrow up capture and type over. It's up to you how you want to deal with it, but I'm going to go with it this time as a type over. Okay, so our total that we need is 11 out of 11. Now let's go down and let's say our first one, let's type in one of the 4s. So it's 4 out of 4. And then next, let's do 4 again. Oh, we already have it typed in 2. So let's leave the 2 and arrow over and multiply and add another one. Alpha, another permutation setup, which is number 7 again. Right now we can do our last 4 out of 4. 4 out of 4. Okay, double check because I did type over and it's easier to make mistakes when you do a type over. All right, 11, 4 out of 4. Looks like everything looks copacetic. So let's push enter and see what happens. All right, that is option B. Nice. Okay. Now, number 3. A restaurant has 2 different soups, 3 main courses, and 5 different beverages, with a meal deal consisting of one item from each category. Okay. Suppose chicken soup is one of the soups and coffee is one of the beverages. If you order one soup and one beverage, what is the probability that your meal will have chicken soup and coffee? Okay, this is a little bit trickier, although it is simple probability. And we have the word and. Okay, so that means we're multiplying. However, we have a situation with soup and coffee, but not with the main course. Okay. This is how we need to set it up, or we need to consider it in a certain way. All right. This is what we need to consider. It says chicken soup is one of the soups, and coffee is one of the beverages. Okay. Well, what we need is for the chicken soup, we're just going to take one out of the 2. Okay. And then for the beverage, we're just going to take the probability of 1 out of how many? Let's see, beverages, we had 5. 1 out of 5. All right. Now, we need to talk about this main course. They didn't talk about it. They didn't even talk about the probability. All we know is, or we can assume, that in the meal deal, there's just going to be a main course that we know we're going to get one. There's no condition, there's no questioning it. So in this case, we need to realize that we're talking about the 3 out of the 3. Oops. So this means that it's just 100% that we're going to get one of them, and it doesn't matter which one. Okay? Now, looking at that, what's really going to happen? Okay, we really have to think through this question carefully. It's going to reduce down for us exactly the way we want. Okay? What's going to happen? Well, if you add up all of the possible combinations, right? You're really going to add the well, I'm sorry, but not add them up, multiply them. All the possible outcomes. Well, 2 times 5 is 10, 3 times 5 is 30. That'll give you all your possible outcomes. Out of those outcomes, the truth is we have to multiply. Well, only want one out of the soups. We only want one out of the drinks. But you know what? It doesn't matter which of the three we get. The probability of getting one of them is 100%. So we're just multiplying all that times three. Well, obviously you can reduce that, but let's say we didn't write all this down. We could have just put this in our calculator. Okay, and I'm going to say alpha window. Oh, no, no. I'm going to go over. It's not window. Every time I make that mistake, I need to arrow back. Anyway, it's y equals, but you can arrow back and forth. If you haven't played with your calculator, you can go back and forth. Oh, interesting. You can go back and forth. That just popped me out of it. Okay. Alpha y equals. Okay. Doesn't matter. You can go back and forth. So let's push enter because number one's what we wanted. This is what I wanted to show you. If we were thinking about it, well, I know I have all my possible outcomes. I could go ahead and just put those in. I had two soups, three main course, and five beverages. I know that. Well, there's all my possible outcomes. Out of those outcomes, I want one specifically out of one category, one specifically out of the other, but I didn't want out of the main course, I'm not going to specify. All three's fine. So that's just times three. Okay. You really have to think about what is it they're asking me and how could I put that in this real world situation. So that being said, what really matters in this case is it not the one that we're getting out of each one. It's really the fact that it didn't matter which main course. So the impact honestly comes from the main course in a sense because all three are okay. All right, we're not going to specify on one in particular. All right, now let's push enter. And that reduces them automatically to 1 over 10, which we can see option C. You probably already knew that that's what we were going to come out with. Okay. All right. Now, looks like we have something new going on here. This is permutation probability. Well, quickly, let's take a look. Looks like we have a situation where we have the part out of total. We have two parts and their permutations are multiplied together over the total permutation, a permutation of all the outcomes. Okay, so let's look at number 4. Consider the letters in the word speaking. If the letters are placed in a jar and drawn one at a time without replacement, what is the probability that all three vowels will be the first three drawn? Okay, so what's going on here is one, it's probability. Okay, that's different from what we were asked before when we had the word banana and you had repetition. Okay, we were asked, they were asking for total outcomes. What are all the arrangements? What can happen in total as we line them up? That is not what's being asked here. They specifically said, what is a probability? So it's almost like we're flipping things over. Okay. So that is a part at a total, which means it's probability. And our total will be, well, let's see, how many letters do we have? 1, 2, 3, 4, 5, 6, 7, 8. And we have a specific arrangement. Okay, and it also says without replacement. That automatically implies permutation, not a combination, a permutation. So we know how to set that up. Now let's look at the numerator. Well, we have to take the permutation of desired outcomes, what we want, and then multiply that to what we do not want. Well, let's see, there were 2, 4, 6, 8. So n equals 8. Let me count that again, 2, 4, 6, 8. So we have 8, but from that, we're only interested in this 3 here. So we could say that that would be our desired is P. So P equals 3. Now this implies that Q equals 5. All right, so let's set that up in our calculator. So alpha y equals, okay, and then we want uh, alpha window. We want number 7, and we'll start with our P. So that'll be 3, arrow over 3, arrow over, let's multiply, and then alpha window number 7, and that'll be 5 out of 5, 5 out of 5. So what we have is we're taking our two groups that are the part. We take our total, split it into our two groups to be multiplied together. That's our part. Those are the two parts we're talking about. And then we divide that by the total. Okay, so let's arrow down and do that. Alpha window. Okay, and number 7 again. And now we have 8 out of 8. 8 out of 8. Push enter. Let's see what happens. Oh, before I push enter, let me make sure I typed it in correctly. Yes, I did. Okay, let's push enter. And 1 out of 56, and that would be option B. Number 5. 6 people are assigned to 6 different seats. Suppose that these 6 seats are in a row and assignments of the seats are random. If 2 of the people to be seated are K and J, what is the probability that one of them will be assigned to the first seat and the other will be assigned to the sixth seat? Okay, there's information in here that we aren't going to care about. Okay, first off, the names of the people. No one cares. What we do care about is that there are 2 people. That's what's important in this situation. So let's take a look here. Well, we have total of 6 people. So our total is our N. And then we care about 2 people. Well, that's going to be our P. And then obviously the other 4, they're not our primary concern. They're not our desired seating per se or people to sit. We just want to worry about K and J. Okay, well, that's our Q, and that's going to equal 4. So what can we do? Well, we can use our prior setup. Okay, so that's going to be the probability, which would be the permutation, rather, the permutation of the 2 that we are concerned with, and the times the permutation of the 4 we're not concerned with. That's our numerator over our total permutation of the 6 people. Let's put this in the calculator, okay? And while we do this, let's think about this. We don't care about K and J, okay? But, or rather, that means we don't care about which one they seat in. Why not? Because of the words in the problem. The problem says, here, let me highlight this really quick. Okay, it says random. Okay, that means, yeah, what's probably the first seat, the sixth seat? Well, it could have been the third seat and the fifth seat. It doesn't matter. It's all going to come out in the wash. Well, let's see how this happens, okay? All right, we need alpha window. We need number 7. Well, let's see here. We are concerned about K and J. So that would be the 2 out of the 2. Arrow over. That is times. Now we're going to do our other 4 people that are not our primary concern. So that will be, all right, that is alpha window number 7 and 4 out of 4. Okay, all over our total probability. Okay, so that's again alpha window number 7, and that is 6 out of the 6. Okay, so again, this is what we're looking at. We're looking at a probability. So we have to multiply the outcomes of our two groups that we've pulled out. We've taken our total, we've separated them into two groups, the group of what we're concerned about and the group that we're not concerned about. Okay. And then we put that all over the total. Okay. Total permutation. All right. Let's push enter. And that is 1 out of 15, which is option B. Well, I'll change colors here. Well, that didn't help much. There we go. All right. Now let's look at the next question, number 6. Now, number 6 is a little on the intense side. And let me read that so you see what I'm talking about. Okay. Great. It says in a movie theater, there are 10 seats in a row and there are 10 rows. Two friends are late to their movie. What is the probability that the two friends will be seated next to each other? My first thought was, well, you shouldn't have been late. But anyway, that doesn't matter. We have a couple options for our late moviegoers. Okay. First option is this, and I'll use our little setup, our little diagram I kind of have here. First option is, well, one, they move it, rather not move in, they walk in to the movie, let's say one at a time, one ahead of the other. Okay. Well, the first friend, he can either he gets lucky and sits down. His seat is on an end row. Okay. He gets lucky. And then the friend after him also gets extremely fortunate himself or herself and gets to sit right here. That'd be great, right? Okay, well, that's talking about end rows. Okay, so let's set up uh, that first scenario. Okay, so let's say that okay, we have okay, that would be 20 end rows because there's 10 rows. Well, 10, that'd be a column. Okay, end row. So that's a column of 10 and a column of 10. So that's 20. But that's still 20 out of the 100. You have to remember that. Okay, and that person sits down. And then we said the second friend gets lucky. Okay, and comes in. Now you got to remember, the first friend has already sat down. That means there's only 99 seats total. But out of that 99, we only want one of them. Okay, he's limited. Wherever that first friend sits, he's got that one choice. If he sits somewhere else, then he's not sitting by his friend. So that's why it's 1 over 99. Okay, and then we have another scenario. Well, that would be or. You can have one or the other, but not both. So that would be addition. But now we have to set up the next situation. Okay. Well, what's really going on? Well, let's change our highlighter here. Something a little different. Let's go with the green. Well, let's say the first friend doesn't sit on the end. Well, they're forced into picking something else in the middle. Okay, they're out here, or in here rather. This is what they had to settle with. Okay, this changes everything. Okay, I'm going to color this in a little bit better because I have to kind of mark on it so we get an idea. Or you may have already figured out what's going on here. What's going on is if they sit here, anywhere in here, okay, all right, they walk in, da-da-da, here they come, and let's say they got lucky here, and it's a little closer to the screen. He's like, oh, okay, I'm going to sit right here. Okay. But then the friend comes along. Where are they going to sit? Now they have to sit by the friend. Well, this means they have two options. They can sit here or they can sit here. And that's pretty much true about anywhere in the inner seats. Okay. Either way. And remember, we're talking about rows. It has to be in rows. You cannot sit in front or behind. That's not sitting next to the friend by definition. Okay, so what does this mean? Well, in the inside, there are 80 seats. So that means that we have 80 out of the 100 times, well, there are 2 seats out of the 99 left that the second friend can sit in. Okay, now let's pop that in the calculator, all right? Well, we have alpha y equals enter. Well, that's 20 times 1, and I'm going to go ahead and type it in because I want the visual. Okay, you don't have to. You could just say 20. All right, now that would be over 100 times the 99. Let's scoot over. That's our first situation all together. Now let's push add and alpha y equals number 1. Okay, now this is different. This is 80 times 2. Oops, there's our 2. Okay, and again, the numerator is the same. Now you can see where I could have even typed that in a different way because you know the rules of denominators. We have a common denominator. But this is a visual so you can understand what's going on. So I'm going to leave it like that. Okay. So that being said, let's push enter and see what we actually end up with. 1 out of 55. And that is correct. And I double check this with several sources, books, internet, everywhere. And I know that it is actually correct. And the way I explained it, I absolutely convinced myself that that's just what you have. That is absolutely your options, but it's all implied. Just like a lot of these questions, you have to sit down. So when you're taking your test, do me a favor, sit down, draw each of these items out, just like I drew them. Just very quickly do some boxes and put some little marks in it so you know in your mind, hey, I've got this correct. I've seen someone show it to me before, and now I've copied what they've said, and I know that my calculator can give me the right answer. And I really hope this was helpful to everybody. And thank you for watching, guys. You guys are the best. I got another very positive comment on the internet. Thank you to those people who sent me your wonderful comments. You are the best. And thanks for sharing and liking and subscribing. Happy testing, everyone.